two specific infinite series, the first of which is going to be the geometric series, which we're going to talk about right now. So the definition's up top here. So if we have a geometric series, it's a series of this form. So it's an infinite series from n equals 1 to infinity, and we've got some constant a in front of it and some other constant r that we're going to raise to the n minus 1 power as n goes up. So if n is 0, n is 1, we get 1 minus 1 is 0. Anything to the 0 power is 1. So we've got a situation where we're at just a. And if our n goes to 2, 2 minus 1 is 1. That just gives us r back, so we're at a to the r. For n equals 3, 3 minus 1 is 2, so that r will be squared and so forth. Now your a could be anything, but if it's 0, well, this is not really interesting, is it? Because if you have a is 0, well, then we have 0 plus 0 times whatever r is plus 0 times whatever r squared is. So generally we don't do that, but that's okay. Couple things about this geometric series. If your value r is less than 1, strictly less than, or more to the point your absolute value is less than 1, then you're going to converge. And it's going to converge to this thing over here, whatever your a was on top, and then 1 minus r in the denominator. And again, that's for the absolute value of r less than 1. Why is that? Well, let's pick an r value that's between negative 1 and 1. Let's choose an easy one. Let's choose 1/2. Let r equal 1/2. And so we'll just use the same old a. We'll just use a and not worry about that. So the sum of n equals 1 to infinity of a and then 1/2 to the n minus 1. Well, our first value is going to be just a again. There's no difference, right? And then we get a to the r, or a times r, a times 1/2, or a over 2. And then we'll have the third value, so we're going to be squaring it, a times 1/2 quantity squared. Well, this gives us a plus a over 2 plus a over 4, and the next one will be a times 1/2 to the third, and that's eighth, so a over 8 and so forth. So what's happening to this? Well, it's getting really, really small. We know what happens with a limit if we're only increasing the denominator. It's getting very, very small, and it's getting small pretty quickly. So eventually our value is going to approach 1. A over something very, very big is going to be equal to 0. So, and if I said 1, I didn't mean that. I mean 0. So these things we're adding are going to be smaller and smaller and smaller until they approach 0. So that's how it shows it converges. Now what it converges to is this a over 1 minus r. So in this case, it would be equal to a over 1 minus 1/2, which equals a over 1/2, which equals 2a. And this should not be difficult to understand. So you get the full a first, and you're going to approach the second a. So what happens when you cut something in half? You cut something in half, and you're at 50%. And you cut it in half again, you go to 25%. You cut it in half again, you're at 12.5%. You keep cutting it in half and half and half and half, and you never actually get to the 0. But you also never get a full 1. So that's why we get our 2a is what it approaches. It doesn't actually ever get there, but that's what essentially it converges to. All right, so I guess the last thing to talk about this, if we have the absolute value of r greater than or equal to 1, it's going to diverge. So, even if it's just 1, we have a plus a plus a plus a plus a. And unless that a is 0, it's going to diverge to either infinity or negative infinity. So, and again, we're not typically dealing with a's of 0. All right, let's take a look at number 99 here, and let me erase some of this work here. Let's erase the example so we can have some room to do number 99. Okay. So number 99, we're taking, we're using the identity 1 over 1 minus y is equal to the sum, the infinite sum of that y to the n. So it's removing the a entirely. So it's assuming a is 1. No problem. We're going to express the function as a geometric series in the indicated term. So the indicated term in here for number 99 is sine of x. So we're going to try to turn everything sine of x. Well, they give us a problem that's already in sine of x, so we can do that easily. So we have 1 over 1 plus sine squared x, excuse me. All right. Now, we need to put it in the form 1 minus y in the denominator. So I've got a plus there. So what can I do? Well, this equals 1 over 1 minus a negative sine squared. Not bad, right? Okay, so we have the y. The y is the negative sine squared x. This is our y. So given this formula here, that's going to equal n equals 0 to infinity. Y is we know to be negative sine squared x, raising that to the nth power. Now, instead of ending here, we can do a little bit of cleanup because we can break sine squared and the negative 1 up into 2 pieces, right? So negative 1 to the n power is this. And then we have sine squared to the n power. Well, we have the second exponent raised to an n exponent. So that's going to be multiplication. So that's going to be sine to the 2n of x. And this should be our solution here. All right, so number 100 over here on the left is going to make us do a little bit more work because they want it to be in sine of x. So let's go with, we've got secant squared. Well, secant is 1 over cosine, so this will equal 1 over cosine squared of x. But we need it in terms of sine. Well, we can use the sine squared plus cosine squared equals 1. Or sine squared x plus cosine squared x equals 1. So that means cosine squared x equals 1 minus sine squared x. So here we don't have a negative version, we just have the positive version because now our y is fully sine squared x. So this is going to equal the sum as n equals 0 to infinity of just the sine squared x to the n. And again, we're going to do the same trick. We'll multiply the 2 by the n to get sine to the n of x. So sine raised to 2 to the 2n, not 2 to the n, 2n. All right, easy for me to say, right? So these are a couple examples of how to use the geometric series, what it is, and so forth.